Hello, guys. I'm sure every one of you are doing extremely well. Today, we're going to handle a very interesting problem in terms of the distributed computing and in terms of the general computer science practicality approach as well. That is what a double booking or a concurrency handle in case there are multiple users are trying to access the same resource. So, just let me give you a little scenario. As you can see, this is suppose just think that this is a book my show. This is a book my show UI for a ticket booking of a certain movie or a certain game, whatever is going on. Now, there is this user one is trying to book this seat, and at the same time, the user two is also trying to book the this same seat. Okay. So how we are going to handle this kind of scenario, and this scenario of multiple user booking of a single resource can happen for any case. Just think in terms of like it can be like you are booking a ticket in a stadium or even for any bus. IRCTC handles it really well. IRCTC doesn't give you a concrete seat that you can choose. It has its own algorithm behind the scene, but the basic principle is quite same. Like if two requests are coming uh, at the same time for a single resource, it there is a way it can lock that resource or it can exhaust that resource, and there is not a single way, I would say. There are uh, like a plethora of technique. All of those things we are going to explore in this video. Okay. So just think about this problem in a more organic way. So what are the things that might happen in a normal booking scenario is, suppose there is a certain seat or a certain resource is there. Okay. And suppose there is a certain user is there. Now, the first and the most naive thing that we need to handle is, suppose the user is pressing the button multiple times. Okay. So suppose there is a submit button for booking this seat, and user is pressing mistakenly multiple times. So when this kind of issues are being discussed in probably in your product or in your development cycle, the first thing you will often see a very naive solution that anybody comes up is, let's disable the button the moment the first time it is being clicked, unless until we are getting the response back from server. So suppose this is this is a kind of a button that I am having, a submit button, and this submit button is going to book the seat. Now, the moment the first request goes, what we are going to do is we are going to disable the button and disable the other part of the page to make sure, or take the user to a separate page that wait here to make sure that user doesn't go into a double booking. But even if user does that, okay, instead of just disabling the button, there are multitude of things we can do for a single user scenario. So let's take this single user scenario at first. Okay. For a single user multiple booking scenario, as you can see, single user double booking, or to be more generic, we can say single user multiple booking of a same resource. How we can handle it? So the key to this concept is something called idempotency key. Okay. So idempotency key is idempotency key is something that we are going to attach to our post attach to our post request or our API request. Okay, to our API request. So an idempotency key is some kind of a GUID or a kind of a combination that we generate that will ensure that if for a single user or for that single resource, it will be always unique. So suppose there is a resource of some date, resource of suppose 22nd March 2025, and at some place, and it is being booked by user 1. Okay, so this whole combination will always be unique no matter how many times I try to book it using that mistaken double booking. So generally what we do is we generate a hash based key as idempotency. So every single time if a certain user creates a certain request from a particular date to that particular resource, then always the idempotency key will be same. This is the key takeaway from this discussion. So an idempotency key does ensure that no matter how many times you send the request, the result will always be same. And suppose a customer, and just to reiterate again, suppose a customer enters into a details and he pressed into the submit or a continue button, however it is, a unique key based on unique hashed key, I would say, based on username, resource type, or a resource ID, I can say, that particular resource identifier it is trying to book, uh, date and time. With this particular unique combination, a hash key is being generated, and if user mistakenly submits 2 times, 3 times, or n times into API, the API will come to know that the idempotency key or the reservation ID it already exists, and it will only process it 1 time. So this is basically, as we are discussing, the BookMyShow or IRCTC, they are being called a fixed quota system. So I will, for a fixed quota for a given resource quota, I will always uh, generate for a singular resource quota, I will always generate a idempotency key. Now, let's try to come to the bigger problem in the hand. That is when multiple user is trying to do double booking, and this is one of the most talked about problem in terms of the concurrency handle. Whenever we are uh, handling uh, any kind of a fixed quota system, like this is of not much use for suppose a ad aggregation platform or suppose a monitoring platform, but again different platforms provide different guarantee, different in terms of the system design. So here what happens is, suppose two users are trying to book the same movie theater seat at the exact same time. Now again, these two users these two users in the question are trying to book the exact same seat on the exact same movie theater for the exact same show and at the same time. Okay, so like at 10, o- 10 at 10 o'clock in the morning, both of these user 1 and 2 are trying to access this or book this resource at the same time. So can a similar idempotency key approach will help? So this is my question to you. Just pause this video and give it some thought. Can idempotency key help here? Okay. So if you think carefully, the answer is no, because here you see the username has been one of the distinguishing factor, but in this case the usernames are different. So what will happen in this case is, the because the username is different, so the idempotency key will be different. So again, one of the most naive solution that we can have over here is, the first solution that comes to any engineer's mind is to apply a lock at the application end. But a lock will not help here. Why? Let's look into this. Suppose the lock always have a application context, right? A lock works on application context. Now, suppose in our distributed system, this BookMyShow application is hosted in two different application server behind the load balancer. Okay, so just to make it a little easier for you to understand, suppose there is a load balancer, and what this load balancer does is, based on the user's request or user's location, it will take the user to two different application server. Now, suppose because of the high load, this user one is actually making a request here, and the user 2 is making a request here. Now, as lock works on the application context, so in a distributed scenario, what will happen is this lock will not work, because although user 1 will be locking the instance on this application server A1, suppose, okay, in application server 2, in the distributed system, that lock will not be there. So lock will be here, but no lock here. So our code can run into that particular block which is doing this operation for that particular reservation ID. And I want you to explore more on this question. Like, you can pause this video and just see why distributed locks are required. So I will not into the discussion of distributed locks. That's a different thread of different thread of system. But I would like you to explore. I would request you to explore that why distributed locks are required over here. So if you get that idea, it will it will be completely clear with your concepts that why a single that what is the difference between the application level locking, or what is the difference between the mutex, why this kind of locking will not work here. Okay, so considering we have a database where all the queries for a single movie theater or a show will point to a single database is coming. So in the application end, we cannot do anything. But again, considering we have a database, now I will just copy paste this text for you. Considering we have a database where all the queries of a single movie theater coming, we can apply locking at the database end. So the idea is not in application end unless it is a distributed lock, but in database end. Again, considering that database is a single instance database. Okay, so if again it is a distributed database, that will be a different set of a problem. But let's consider uh, it has a single instance database there in a place like BookMyShow TV booking for a single theater. There is a single database where this particular resource is existing. Okay, so what we can do here? So there is something called a for update clause. Now we are going into the nuances of the RDBMS. So what that does this for update clause do? So this for update clause in SQL, it is used to lock specific rows in a database table, so other transaction cannot modify those rows until the current transaction is completed. Okay, so if I can just if I can wrap something under a transaction, suppose take it for a room booking website. Okay, for a room booking case, if this transaction I am picking up and I'm marking it for update, then I am telling the database system that do not do not even show it to any other user. Okay, so while I am keeping it for update, this room 101 will not be even shown, because it is no longer available for the other transactions to modify. Okay, so just to iterate again, imagine you are building a hotel reservation system like Airbnb or booking.com, you have a limited number of rooms and multiple users are use trying to book the last available room at the same time. If two transactions check the inventory simultaneously, so suppose I have this the last room, and again I will take these two users, user 1, user 2. Suppose this is the last room, user 1, user 2. At the same time, they are trying to book the last available room. So if they check the if they check the inventory, they will see that one room is left. Both might try to proceed with the same operation of reserving the room. Okay. So what will happen is from here, both will initiate reserve of the room. Reserve of the room, and it might get into overbooking. So how what will happen is I will just show you this thing a little bit with more details. Suppose in the same time, as you can see over here, this time parameter we have, in the same given time, what the user 1 is doing is it checks the inventory. User 2 also checks the inventory, and they see, okay, uh, let fire the reserve room function, and it see that there is a total reserve of 100, and it will also see that there is a total reserve of 100, and then they will commit. Okay, so now what will happen is we will it will result onto overbooking. So this is the exact overbooking condition. Now what will happen with the for update? So how for update will save this flow is, you see, there is a user 1 at the same time frame. He checked the room for the inventory with form update. For update, there will be one room left, and it will be locked. Now we will come to this implication later. What will happen when a certain record is locked? But just bear with me for this time. A particular record I am just locking. Okay, and this transaction for this given time, you see, for this given time, this transaction will nothing but just wait. Okay, and once the commit happens, then only the lock is getting released. Once the commit happens, this is a very important factor. The lock is released only once the commit happens. Okay, so once the lock is released, then only it will go and check the inventory, and what it will see is that inventory is because it is selecting it for update, that inventory is giving that no rooms are left, and so eventually the transaction will fail. Okay, so let's see how overall in a query it will look like. Okay, so let's see here the RDBMS query, how it will look like. So RDBMS query would look like something like this. So at first we are going to wrap it under a transaction. So this is one of the main thing. The whole thing needs to be wrapped under a transaction. I forgot to copy that end part of the transaction, but what will happen is like there will be also a end at the like once this transaction is completed. So once we are doing the begin transaction, this whole thing will be a atomic transaction, right? Going back to your basic ACID property. Now what will happen is select star from rooms, and it will check the reserve count, whatever the current reserve count is, the plus one should be less than the total inventory, and assume that room 101 is returned by the above query, and because it is going for the for update, um, here the reserve count, just one more clarification. So the reserve count is this reserved count variable represents how many has been reserved so far. Okay. So what will happen is, in this case, this reserve count variable plus 1 should be less than my total inventory. If it works, then only it will go ahead and uh, update the rooms. So as you can see, like if there are if two transactions are there, as we can see over there, that suppose when rows are locked using for update caused by transaction A, let's talk about the lock a little bit more. Okay, locks in for update. So when rows are locked using for update for a given transaction, the behavior of transaction A, suppose, so transaction B depends on the locking of transaction A. So transaction A and B, when I say, like, it is the same begin end statement, but coming from a different session or from different users. Okay, so this is one of the very important thing, and this is, if I see, this is a blocking behavior. This is a blocking behavior. Okay, so if transaction B tries to access the same rows locked by transaction A, it will return, it will need to return till the locks are being released. Now, transaction B does not return rows immediately, right? This is kind of a problem of lock, because if there are multiple resources are working in this kind of a synchronization setup, there can be a longer wait time. So to mitigate that, there are something called no wait, and again I want you to explore this thing from the backend, that what exactly a no wait in RDBMS is. Okay, so to make it a non-blocking, like for example, if there are some kind of a deadlock happens there, um, how can we handle it? So no wait is something that we can use. Again, I'm not going into the details. There are few things I am leaving up to your exploration, how we can use this no wait. But taking a queue of these logs, I can I can spawn another discussion that there will be plenty of issue with for update in production. Okay, why I'm saying this? While for update restrict access to rows, let's consider this scenario. Okay, so transaction A, what it does is it locks room 101. Okay, transaction B, it locks room 102. Okay, now suppose transaction A tries to book room 102 as well, but it waits because transaction B holds the lock. Okay, so suppose a family of two, basically, like two family require two rooms, two separate family. Two separate families coming, and they require two rooms. So the first family, what will it will do is, this is the for the first family, it will spin up transaction A, locks room 10, also tries to lock 102. And what it does is, this second family also tries to lock 101. Now you see transaction A is waiting for 102 and transaction B is waiting for 101. Now this is a classic deadlock scenario. So this is nothing but a classic deadlock. Anyway, the current RDBMS systems are very much like the modern RDBMS system, I would say. They're very much uh, well equipped to detect this kind of situation and terminate one of the transaction to resolve the deadlock. So that is that is where in production, if we are just blindly applying for update, it can cause plenty of issues. So till now, whatever the approach that we discussed so far, it is basically something known as pessimistic locking. So I would have started in a reverse direction. I could have started in a reverse direction, that what exactly is pessimistic locking, and this is how we do the pessimistic locking. But I wanted to build the intuition. I wanted all of us to build the intuition that why a pessimistic locking is bad for database. Okay, so now that we know that what exactly a pessimistic locking is, uh, and why it is being called a pessimistic locking, because it is causing a classic deadlock scenario. So let's look into what optimistic locking is and how we can leverage, how we can actually avoid deadlock and leverage the RDBMS in a very innovative way to make sure that both of these transaction actually passes through, but one may success, one may fail. So just have a look into the table structure that I am changing right now. Earlier, probably you remember there was only seat ID or the status that we were handling. Now a new column that we have added. That column is this version column, and you see here it is. I have also mentioned that it is a optimistic locking version number. Okay, so how this version number will come into play, we will discuss in few minutes. But before that, let's take a scenario based approach, like why uh, and how this version number is going to help us in case of that double booking scenario. So suppose a similar that one seat is left, okay, with seat ID 1 with a status available and a version number 5. So a given seat of 5 is having a version number of 5. Now what this user will do is, it can be version number or it can be a, like some kind of a date number, anything it can be. So what this user will do is, the user one will initiate his transactions. Okay, so user one will initiate his transaction, as here you can see. At first he will select the version number as well, with the seat ID equal to 1 and probably the availability status also equal to 1, something like that. Okay, so then what he will try to do is, like, at the same time, sorry, the B will also probably have done the same. Now, the moment they are updating the seat, what they will do is, they will increment the version number. So suppose the version number here was 5, what it will become? The version number will become 6 in this case. Okay. So suppose this is 5. So it it suddenly becomes 6. Now you see this user B queries. So now we understand this part, right? That our version number at this level is from 5 plus 1, it is 6 now. Now if you see the query of B, what it is trying to do is, what it is trying to do is, it is trying to book the same seat in this way, where it is trying to apply to this version number 5, right? And this commit and rollback are actually optional, you can just mark it as an end. So what will happen in this case is, because it is trying to get the version number 5, it will not get that version number 5 because we have incremented the version number over here in this particular case. So this is the core of the optimistic locking, and advantage over the pessimistic locking is, like, if I have to just document it, the advantage over the pessimistic locking is, pessimistic locking no way we can get into a deadlocked scenario. Okay, so we are not going to get into a deadlock scenario, but it is still a problem. It is still a problem considering that suppose we have a high cohesion or a high contention system, suppose. Okay, so high contention system means that uh, too many transactions are going on. Okay, too many transactions are going on, and the system will have so many transaction failures. So here we are basically failing this transaction, right? If we see this case we are failing this transaction. This is a failed transactions, although no exceptions or nothing is there. So for a high contention system, suppose you have like a very uh, like maybe in a single seconds 1 lakh transactions are going on in some way in your database. If you keep on doing this sort of versioning check, what will happen is here we might get into so many failures that retrying those failures will bloat up your system a lot. Okay, so to mitigate that, there is uh, there is a very usual way that we follow, that is being known as the database constraints. Now again, by leveraging RDBMS properties, we are going to have we are going to use database constraints to prevent overbooking. How? So this is why RDBMS is so beautiful. There are so many properties it gives you, which is lesser known, but we can leverage all of them. So let's discuss about this query now. Okay, not a query, schema definition, I would say, like a DDL statement. In this DDL statement, what we are doing is we are defining that for this room type inventory, for room type ID int primary key, the total inventory and what will be the total reserved, and total reserved, this default zero, all these things you can ignore right now. Alongside all of these things, we are having a constraint on top of this create table, that you always check that the total inventory, whatever the total inventory data you have, minus the total reserve, that should be greater than equal to 1 during any operation. So what we are doing is the DB constraints is telling us that check or enforce business rule that the that any transaction on this table should not violate the this rule of total inventory minus total reserved. But you see, there is one problem to this approach is like we need to store the total reserved and we need to keep it calculated every single time. Of course, that is something that we need to take care during our update statement. However, what generally happens is like if I just try to take the use case. Suppose there is a room ID 1, and for that particular room type ID, the total inventory is like, as you can see over here, is 100, and the total reserved is marked as 99. So when a user B start the transaction, he will always see that so not he, the database will always check whether uh, whether this condition passes or not. For example, if user A starts a transaction, this update room inventory, the database internally will always check that if the total inventory minus the total reserve is greater than 0 or not. If it passes, then only it will let the transaction go. Now coming into at the same time, if user B suppose fires a query, what will happen? Let's see. If user B fires a query at the same time, what will happen is, because already this total reserved has become from 99 to 100. By the time the user A have done it, suppose it has already become 100. So this, like when it will try to book, the total reserved in this case will become 101. And so what will happen is, this total inventory minus total reserved will not be greater than equal to 0, rather it will be minus 1. So our database will completely fail this thing. Okay. Now, of course, this is again a kind of a scenario based fix, I would say. This has a good amount of performance impact. Like, why it is a performance impact? Like, if you have worked RDBMS for a considerable time, you will understand one thing: frequent constraint check. Okay, so frequent constraint check actually slows down the high highly concurrent system, because anyway, end of the day, this this is being checked implicitly, but this is being checked, right? So this frequent constraint check highly concurrent system. So end of the day, this check has to be done on the every single transaction that is happening over there. Okay, so any delete happens, or any other update sort of things are happening over there, or any even create new record or anything that happens, on all the cases we need to check this scenario. So considering that fact, it might lead to some kind of a performance bottleneck. So during peak booking hours, suppose thousands of users are trying to reserve the room simultaneously, and when database enforces this kind of check, it will definitely slow you down. So this much are, I would say, basically pretty much what we do these days in terms of the locking or handling the concurrency on a very conceptual level, and I have tried to keep it as practical as possible in terms of the RDBMS. As you can see, like all these RDBMS queries, I have fired over, like whatever we can fire over here, I have written, and the similar thing we can achieve in our NoSQL or any other kind of database as well. So this was the video, guys. The My one request will be, like, you please explore one additional thing: why distributed lock is required. This is a completely separate, over application lock, why distributed lock is required. This is a completely separate discussion, so I haven't gone deep into it. I have given you a very high level idea what are the problems that like a application level lock or the mutex can lead to, which distributed lock might help. But again, this is a great point to explore as a follow up to this video. So in case any point is not clear to you, please do put your questions on the comment. I will try my level best to answer that. Thank you so much.